Hey everyone, welcome back with a new lecture with how to calculate measurement uncertainty for microbiological measurements. In the previous lectures, I have explained that you can calculate uncertainty only using technical uncertainty by reproducibility. You will calculate at the end the reproducibility standard deviation, because technical uncertainty from reproducibility will include also matrix uncertainty and distributional uncertainty. And also I said that matrix uncertainty refers to the effect of microbial distribution in the test sample. So by taking different test portions by different analysts, you will have different results, and this variation between results refers to the matrix effect. And also you can calculate uncertainty by the other option, by calculating individual uncertainties: matrix uncertainty, distributional uncertainty, and technical uncertainty, and calculate or combine all of them. But that may overestimate the uncertainty, the overall uncertainty at the end. Distributional uncertainty due to random distribution of microorganisms in the test sample and also for subsequent dilutions, even for homogeneous samples. And there are three kinds of distributional uncertainty, as I explained before. For colony count techniques, we have two types of uncertainty. First one, uncertainty, Poisson uncertainty. By counting the colonies, you will have to calculate uncertainty Poisson uncertainty. And confirmation uncertainty if required. If you will make confirmation for the analysis for colony count techniques, so you have to calculate also uncertainty for confirmation uncertainty. And another additional uncertainty component for most probable number based methods. You will calculate uncertainty for most probable number. First type of distributional uncertainty for colony count techniques, uncertainty Poisson. For methods based on colony count techniques, there is a minimum distributional uncertainty determined in ISO 19036 in a specific table for that contribution, depending on the total number of counted colonies. After you will count the colonies for test portions for each sample, you will calculate the total number of colonies counted. Then you will calculate the uncertainty Poisson. You will find this determined in this table. You will find this table and you will add whatever written in this table. For one number of colonies counted, total number of colonies counted 1, uncertainty Poisson equal to 0.434, and so on up to 40 colonies counted. You will not find more than this in the table. So what about other or larger than 40 colonies counted, 40 total number of colonies counted higher than 40? For this, they write also another equation, and you will find this also in this ISO, in this document. For colonies counted higher than 40, you will use this equation: uncertainty Poisson equal to 1 divided by function n of 10 divided by square root of number of colonies counted, which equal to 0.4343 divided by square root of total number of colonies counted. As here in this example, for total number of colonies counted 100 equal to 100, you will calculate 0.4343 divided by square root of 100 equal to 0.04343, and that will be the uncertainty Poisson for 100 colonies counted. And they mentioned also in this document, and you will find all of these documents and tables and Excel sheets for calculation in the resources, and you can download all of them, and you can find the tables in this document. They mentioned also that for larger numbers of colonies counted, uncertainty Poisson or distributional uncertainty may be negligible if other uncertainty components are large. The second kind of distributional uncertainty is confirmation uncertainty. For some methods based on a colony count technique, you need to make confirmation after counting of colonies, because these methods, some methods based on a colony count technique, these methods will give you a presumptive numbers of organisms. So number of tested colonies, as example, were 100 counted colonies. But this is presumptive number, so confirmation test required in this case used to correct that by estimating the proportion of a selected number of colonies. You will not make estimation for all number of colonies counted, but you will make confirmation for a selected number of colonies. As example, for 20 colonies counted. So from 100 colonies counted, you will estimate some of them. So proportion of a selected number of colonies, that's already confirmed as the target organism using appropriate test. So at the beginning you will count the colonies, and it will give you, this method will give you a presumptive number of target organism. Then you will make confirmation for by estimation a selected number of colonies, and you will find, you will have number of tested colonies and number of confirmed colonies. And from a specific table in ISO 19036, you will find table number of colonies tested and number of colonies confirmed, and in front of both of them you will have the uncertainty for confirmation, and that will be added to the combined uncertainty. So you will calculate the number of colonies and number of colonies confirmed. You will have number of colonies tested or counted and number of colonies confirmed. And from table found in ISO 19036 also you will find uncertainty for confirmation as here in this table. So suppose presumptive colonies NP are tested and a number of them, estimate a number of them are confirmed NC. So from this table, uncertainty confirmation values in log 10 for selected values of colonies tested NP and number of colonies confirmed. So NP here and NC here. In front of 5, if you have number of tested colonies 5 and number of confirmed only 1, so uncertainty confirmation will be this number. And in the table you will find up to 5 number of colonies, 5 number of colonies tested and 5 number of colonies counted. And same for 10, you will find 10 number of colonies tested and 10 number of colonies confirmed. In front of each one of them you will find the uncertainty for confirmation, and also I will show you this table when I will calculate using the Excel sheet. But what about other number of colonies? If you have more than 20 or more than 20 number of colonies tested and number of colonies confirmed, what you will do in this case? And they mentioned also this in ISO 19036. For other numbers can be calculated from this equation. Uncertainty confirmation equal to 1 divided by 2.303 square root of NC number of colonies confirmed plus 0.5 multiplied to NB minus NC plus 0.5 multiplied to N square P divided by NB plus 1 square multiplied to NB plus 2 multiplied to NC square. And this equation came from ISO 29201 2012, and I will explain how to calculate also in the Excel sheet this equation. I calculated also, I added to the Excel sheet, and you can find this in the resources. So what if you have number of colonies confirmed less than 1, 0? Number of colonies confirmed was less than 1. In this case, you will calculate uncertainty confirmation from the table also as NC equal to 1. The third and last kind of distributional uncertainty is most probable number uncertainty, and that will be for most probable number based methods. Most probable number technique has been explained in details in ISO 7218, and in this technique several inoculation from each test portion are inoculated separately into different aliquots of a growth medium, and the result will be either positive or negative, so qualitative. You will get positive or negative. So some most probable number tests require confirmation of the presence of the target organism in every presumptive positive. You need to make confirmation for every presumptive positive. So calculate most probable number and its uncertainty from the number of confirmed positive results from this table. Here you will find number of wells giving positive reaction, positive results, 0, 1, 2, and in front of each one of them most probable number per 100 ml sample. You will find this number, and here 95% confidence level lower and upper, and log 10 standard deviation, which is the distributional uncertainty, and relative standard uncertainty, and this number will be used as the uncertainty for most probable number. So as example, for two positive reactions, distributional uncertainty for two positive results, you will find distributional uncertainty 0.2768, that will be used as uncertainty for most probable number. All of these tables will be explained in details after that using the Excel sheet for calculation. And combined uncertainty, after you calculate technical uncertainty, matrix uncertainty, and distributional uncertainty. In distributional uncertainty you have Poisson uncertainty, confirmation uncertainty, and most probable number uncertainty. Then you will calculate combined uncertainty by combination of all of them, combining all of these uncertainties, maybe based on one of the following options. First one, combination of separately estimated technical, matrix, and distributional uncertainty. After you calculate each one of them individually, so you will combine all of them individually also. So as here, for colony count techniques, uncertainty combined equal to square root of uncertainty square of technical uncertainty square plus matrix uncertainty square plus Poisson uncertainty square plus uncertainty square for confirmation also, if there is confirmation. If there is no confirmation, you will not add this one. And for most probable number methods, uncertainty combined equal to square root of technical uncertainty square plus matrix uncertainty square plus most probable number uncertainty square. Then second option, reproducibility standard deviation. If you only calculate technical uncertainty by calculation of root deviation of intra-lab reproducibility, then you will combine only technical uncertainty square root of a technical uncertainty square. Finally, you will calculate the expanded uncertainty, which is the overall uncertainty that will be added to your result. Uncertainty equal to 2 multiplied to combined uncertainty at coverage factor K equal to, which is at confidence level 95%. But why did we select 95% confidence level to be used for calculation of expanded uncertainty? As you can find here in this graph, normal distribution or Gaussian distribution. In this graph, characterizes the probability of random quantity. What does it mean, confidence level? Confidence level, as I said in the beginning of this training course, how much you are confident from your measurement result. So by increasing the confidence level, the probability of random errors or random quantity will decrease, and by increasing the probability of random quantity, confidence level will decrease. As here in this graph, the probability of random quantity, and here the random quantity, and here you will find the mean. At the mean you will find the highest, half the mean, you will have the highest probability of random quantity. Here the highest probability of random quantity. So probability of random quantity very high in the mean, and confidence level very low, so we cannot use this. And by decreasing as we move in both sides, the probability will gradually decrease, but will never become zero, because zero means zero probability of random quantity means 100% confidence level, and you cannot calculate measurement uncertainty at 100% confidence level, because for every measurement, even the most careful one, there is a probability of random quantity. And then here you will find here at one standard deviation, coverage factor equal to 1. and the confidence level equal to 68%. 68% confident. You are confident only 68% from your result. So you will accept a lot of data which are away from the true value, and this is very wrong. You cannot do this. So this cannot be used. At coverage factor 2 standard deviation, coverage factor equal to, and here confidence level equal to 95%. This is okay. But at 3 standard deviation, coverage factor equal to 3 and confidence level equal to 99.7%, and this is highly restricted. You will reject a lot of data, so you cannot use this and you cannot use this, and it's recommended to use coverage factor 2 at 2 standard deviation, coverage factor 2, which confidence level equal to 95%. So probability of random quantity will be low, will be 5% only. So 95% confident from your measurement result. That was the end of our lecture for today. Thank you and see you in the next lecture.